Welcome to part 6 of making Slither.io using Python programming. And as disappointing as it is to start this tutorial with another paint window instead of code over here, I do want to explain two more concepts about vectors just before I go on to explain how we're going to make the player follow wherever the mouse is on the screen. So from the last time I talked about vectors, I gave a really basic explanation, so this is the player in the middle of the screen here, and if a player wants to move to another position, you have to add that position vector to the player's position. So say this is the position he wants to move to. I think I used this example last time, and it's 10, 10, and the player's at 0, 0 right now. If I want the player to go to 10, 10, he needs to go up 10 units and to the right 10 units. And that's what the vector 10, 10 represents. It represents up 10 units, or I got the order wrong. First is X, then is Y. So it goes right 10 units and then up 10 units. That's what the vector 10, 10 represents. And then I also mentioned last time how in games, you often have to shorten the vectors. If I were to add 10, 10 to the player, he would be there instantly. So if I added 10 to the 0 and then 10 to this 0 here, the player would teleport from here to here and he'd move incredibly quickly. So I mentioned in the last video, we sometimes shorten vectors, and I could shorten a vector to maybe instead of 10, 10, I can shorten the vector to 5, 5. That way the player actually takes 2 steps to get there. But there's an even better way of doing this because that requires, I just divided both parts by 2, but sometimes the math won't always work out that way. Like if I had 10 and 11, it could do it like that, but here's the method I'm actually going to teach for resizing vectors the proper way. The proper way of resizing a vector, and let me undo some of this. The proper way to resize a vector is to shrink its size, and I'm going to use blue for this color, is to shrink its size so that the vector length is exactly 1. And then to control the player's speed, you just multiply this vector by your speed. So let's say my speed variable is 3, and I think we already added a speed variable, but we're going to use it slightly differently. And then you take the speed variable and you multiply it by the vector. So here I have a vector that has the total length of 1. The sum of its x and y, well, that's actually not quite correct, but its length is 1. And then I multiply the whole vector by 3. That is going to then give me a vector with a length of 3. And the reason we do it this way is so that you have more control over your vector lengths and thus the speed of your player. This is better than just randomly dividing x and y by 2, which is what I did in the last video. So the actual method, you shrink the vector to a length of 1, and that's called normalizing. And then you multiply that vector by however fast you want to go, and that will determine your speed. And that's what we're going to do today. But how do you actually normalize a vector? The way you normalize a vector is you use the Pythagorean theorem, and I'll just give the formula for how we're going to, well, first, to normalize, I actually got this mixed up. To normalize, you take the x and the y and divide it by the length of the vector. So I would say the normalized vector, normalized x, is just equal to, and let's use this 10, 10 as an example. 10 divided by the length of the whole vector. The normalized y is equal to 10 divided by the length of the vector, like that. And this would be x or y, they just happen to be the same in this case. That's how you shrink it down to 1, but we need to know what the length of this vector is. And so the way you calculate the length, that's what I mentioned earlier, the Pythagorean theorem. And if you're not familiar with that, I would just say use this formula. The length of a vector is just equal to the square root I'm going to use this kind of like a code notation because I have no clue how to make the square root symbol using typing. So square root of the x squared plus the y squared. That is the length of any vector. So if I wanted the length of this vector, I would take 10 squared plus 10 squared, which is 200, and then take the square root of 200. That's the length of this vector. So if I wanted to normalize this vector, I would divide both the x and the y by that length that's calculated with this formula. And then finally, to resize the vector to match my speed, I just multiply the vector x and the vector y by my speed. So that's the proper way of resizing a vector. The next thing I want to show about vectors before we move on to actually coding is the proper way of calculating vectors. Because as of now, I always put the player in the middle of the screen, which made vector calculation easy. If the player is already at 0, 0, and I want to go to any other point, say this point, which I'm just going to arbitrarily assign -12, 7. Well, I already know right away that to get to -12, 7 from 0, 0, that's what a vector is, it's just directions somewhere. I would just go to the left 12 and up 7, and that would just instantly give me the correct direction vector here. But your player, and in our game, the player is not always going to be at 0, 0, so the math's not always going to work out this way. In fact, most of the time the player is not going to be at 0, 0. Say the player moves somewhere else, and I'm not going to erase this here, but I'll draw a new one. Say the player is way up here. The player is here, and his position is 5 and then 30. And the orb that he wants to head towards is over here, and its position is, and I want to use black for this, its position is 5, or it'd actually be, I'll do 20, 30. Well, I can't, this time the vector is not just 20, 30. That would be from 0, 0 to 20, 30, that would be this. But I want the direction from the player who's over here now, over here to this orb. I want this vector, not this vector. And we need to learn the proper way of calculating these vectors, these direction vectors, because our player is not always going to be at 0, 0. So it's not always going to be as simple as go to the right 20 steps, up 30 steps. We're going to need to do a little bit more fancy math. And the way we calculate this vector here, we want the player direction, we want the direction vector that will take the player from here to this orb. And of course in the game, using this technique, we're going to resize it and give it a speed so the player doesn't teleport there. He'll move slowly there. But for now, we want this vector by itself, not resized. The actual formula for calculating this vector, I'll start with the x. The direction x for this vector is just your target x. Let's use broad terms. X is equal to target x minus start x. And then the y is equal to target y minus start y. Now, what do I mean by target and start? Well, our target for the player is this orb here. This is where the player wants to go, and the starting position is right here. So these numbers here, 20, 30, this is our target, and 5, 30, this is our start. So how are we going to calculate this vector? We're going to use this formula that will give you the vector between two positions. And so doing the math, target x is 20, start x is 5, so my result here is 15. Now target y is 30, and starting y is 30, so my result for the y is 0, and our final vector is the vector 15, 0, which would make sense, because we're not actually, these are on the same level. So we don't need to change the y, we only need to change the x going to the right. This makes a lot of sense. What wouldn't make sense is 2030. That would be this direction here from 0, 0 all the way up here, going to the left 20 units and then up 30 units. That would be different. We're not doing that. We are only going to the right by 15 units. And that's why we need to calculate vectors properly. Not just assuming we're going to start at 0, 0. We need to do it this way because a player, most of the time, will not be at 0, 0. And that is enough for this portion. Now we'll finally get to some of the coding. So right now, the changes that we're going to make are going to be all in player, actually. And, oops, and I left that from last time. I ought to get rid of that, and I'm going to get rid of that as well. All right, so what we want to do is we want to get the player to follow the mouse. So if the player's in the middle, or just wherever the player is, and the mouse is over here, we want the player to calculate the vector from wherever he is in the world, be it 0, 0, be it 530. We want the player to calculate this vector, and we learned vector calculation. And then we need to resize the vector and change the speed, or change its size, which we also learned. So the first thing we need to do is actually find out where in the world the mouse is. And here's how we're going to do that with some of the code I left behind on accident. We need the mouse position. And to get that, I'm going to type mouse pos, mouse position, is equal to, and the pygame function is pygame dot mouse dot get pos. And right now I'm going to pause. That printing code that I cut, I'm going to put that back. And we're going to also get rid of this in a second because we don't want to use WASD, but I'll leave it for now. So right now, I'm just adding print statements that will print the player X and the mouse X. And one more change I made when I was discussing vectors, I added a velocity vector and I updated that velocity vector inside the orb. I commented all of that out so that the orbs don't move. Now when I run it, the player's in the middle. So the player's X registers as 0. However, the mouse's X, I'm going to illustrate a problem with this. I'm going to start moving to the left. So now the player is getting in the negatives. But the mouse still registers at about the same. The mouse, I'm going to pause the game here. So right near the end, I'm going to scroll up a little bit. So the mouse was considered to be at about 500, while the player was at a negative value. But wait a minute, how does that happen? They're at the same X, right? The mouse is right next to the player. Well, here's the problem with mouse.getPosition. That returns that function here, mouse.getPos, that returns the screen position. And remember, the screen position is 0, 0 over here, and your window X, your window width and window height down here. So even if my player is moving to the left and getting into the negatives for my world position, the mouse is still in the middle of my window. And my window, I think I made it 1000 pixels wide. So when I put the mouse in the middle, I get 500. We are getting the window position. But we don't want that. We want the mouse's position in the world. And so we need to do a conversion in order to get the mouse's position in the world. So what I'm going to do next is I'm going to create a new variable, world pos, and we need to convert the mouse position here. So the first thing I'm going to do, I'll start with the mouse's X, mouse pos 0, since this function returns a tuple. I probably should have mentioned that earlier. This function returns a tuple, so mouse pos 0 is the X, but I want to subtract half of the screen width. And the reason I'm doing that is because I want the very middle of the screen to be 0, 0. So back to Paint, and we have all this, just ignore this. So my player is in 0, 0 in the world, but when I put my mouse right here, Pygame thinks it's at 500 since this whole length here is 1000, or at least for my window. So in the middle is 500, and I don't want to get 500. The first thing I'm going to do is I'm going to subtract from whatever the mouse position is. I'm going to subtract half of the window width, and then I'm going to subtract half of the window height. That means that if my mouse is at, let's say that the width of this window is 1000, and let's say that the height is also 1000, and I wish I could remove that. Doesn't look like I can. Oh, yes, I can. Out of room, doesn't matter, you can read it. So this is 0, 0, but if I move my mouse here, the window position is 500, 500. But if I subtract half of the window width and half of the window height, then this middle position will register as 0, 0. So that's what I'm going to type next. So I'm going to take the mouse position 0, or mouse position, or the mouse X, and then I'm going to subtract half of the window height. But we don't have the window height right now, so I'm going to just add that. No, I don't want to add it as a private variable since it makes no sense for player to actually keep it. I'm just going to add a parameter to the update function, WinDims. And we already created that in the main game. We're going to give it that later. So this is the window dimensions, and we'll add it later. Mouse position X minus WinDims 0, and then divided by 2. Like that. So now the X will register correctly. Let's get the Y to register correctly. Mouse pos 1 minus half the width of the screen, WinDims, half the height, excuse me. WinDims 1 divided by 2. So that will mean that even if my mouse is in the very middle, it's not going to be 500, 500. It's going to be 0, 0. So let's print. Actually, this is good right here. World pos. I'm going to replace this with world pos 0. And now let's see what the output is. Oh, and then missing one required position argument. That's because I didn't add it back. So in the main game, where are we calling the update for the player? We're calling it here. All we need to do is add the window dimensions, self.windims. That's where we store the window dimensions. So for the player, I'm just going to add self.windims. Now I'm going to run. And if I put my mouse right about here, it's almost correct. So what output am I getting? I'm getting almost 0, 0, right there. Okay, now I'm getting 0, 0. Perfect. I put the mouse in the very middle, and it comes as 0, 0. But our formula for converting the screen position here to the world position is not done, because now, if I move the mouse, or if I move the player to the left, the player X gets, I'm going to pause. I had to pause the stream and just scroll and find the correct output I wanted so I could show that, so I can make my point. So just because there's so much output. But what I was saying was at the very beginning of our program, the player is at an X of 0 and the mouse is also at an X of 0. But as I scroll down, and again, there's so much output, so this is why I needed to pause. As the player moves left, his X starts to get into the negatives. But the mouse's X does not follow. The mouse stays at 0 because our mouse is still smack in the middle of the screen here. So even as the player moves to the left, the mouse still registers as being at an X of 0 for this screen. And that's because it's not taking into account the world positions. This is a really easy fix. We just got to modify our formula here. All you got to do is add back the player's X position and the player's Y position, and then you'll have the correct world position of where your mouse is. So I'm going to do that. Where we calculate the X, I'm going to add back self.rect.x, which is where the player is. And then for the Y, I'm going to add self.rect.y. And then now we'll take a look at this output. And now I'm going to try to put my mouse as close to the middle as I can. Now, if I move the player, I'm going to pause the output. Now, if I move the player, these numbers are a lot closer than they were. And let's see if I can get it even closer. So I'm going to try to put the mouse right in the middle. That's really close. The mouse and the player are only off by 1. Yeah, so now the mouse is getting the correct world position. The only reason they're 1 off here in the output was because the mouse wasn't right in the middle. But this is the correct formula for getting the world position for the mouse. And now we're able to apply some of this concept here. The first thing we want to do, now that we know where the mouse is, now we can calculate the vector using this formula. I know there's a lot of information here. Using this formula here, we can calculate this vector between wherever the player is and the mouse. Then we will use this formula to resize the vector, then add back a speed, and we'll have the player following that vector correctly. So back to the code. I want to calculate that direction vector. So I'm just going to call it direction, or I'm actually going to call it distance vector since it's just the distance between those 2 points. And so I'm going to make this as a tuple. And actually, I do need to perform math on this even later. So I'm not going to do it as a tuple. I'm going to do it as a list. And so the distance vector, the vector that we're about to calculate, I'm going to calculate using this formula. I need the mouse's x, since that's my target, minus the player x. The mouse's y minus the player y. So let me type that in right now. Mouse pos 0 minus self.rect.x. Mouse pos 1 minus self.rect.y. And now I have the vector that will give you the distance between the mouse and the orbs. And what I'm going to do here is this is actually good enough to get some reasonable output. I'm going to, first of all, delete this since we don't need it. Our mouse world position matches where it should be. So I'm going to delete all this, no more WASD, and no more keys. And like I mentioned, a vector, which we just calculated a vector means nothing until I add it to the position. So I'm going to add it to the player's position. I'm going to add the distance vectors x to the player x, self dot, and you know what, let's use a velocity variable. That's going to be much better. So self dot velocity. Do I really need, I don't think I need to do that. Sorry, ignore that. We're just going to add it right away. I might do a velocity variable later. Self.rect.x. I'm going to add the distance vector x, self.rect.y. I'm going to add the distance vector y. There you go. So what's going to happen here is the player is going to move incredibly quickly. All right, so watch this. So the player doesn't move at all because he is going, right now he's at 0, 0, but as soon as actually, this is a really funny result. I have no clue what this is. He's kind of following, but he's not actually updating his position. What am I doing here? Plus equals, I'm going to pause and figure out what I'm doing wrong. All right, I made a simple mistake. I used the mouse position, not the world position. Remember, the whole point of me getting the world position was so that I could actually make this proper distance calculation. But the mouse position, which is what I was using, is a completely different thing. The mouse position is just the position of the mouse on the screen. So as interesting of an output as this is, what I want is world pos. This is the world mouse position. World pos. And now if I add this, now I'm going to get incredibly fast movement. And we didn't even see any orbs. This is working. The player is moving in the direction of the orbs, but he just moved way too fast because, like I mentioned before, we are adding the unaltered vector to the player's position. Or like in this example, we did not resize the vector, we just added it so the player instantly teleports to where the mouse is. Like this, it jumps. We need to resize it, shrink it down, and then control its speed. I'm going to see if I can possibly run that again. Oh wait, so you see orbs a split second ago, but the mouse just zooms off wherever the mouse is. The player zooms off wherever the mouse is going. So now this is working, but now we need to do just that. We need to resize the vector. So first let's normalize the vector because just a review from before, to resize to prevent this jumping, we need to normalize the vector, which will shrink it down to a length of exactly 1, like this. So same direction, just less speed. And then we multiply that vector by whatever speed we have. So to normalize, I have the formula here. You divide each component of the vector by the length. So let me calculate the vector length. So the length of this vector is just equal to the square root. I don't know if there's a square root function. What I did is I multiplied the exponent operator in Python is just times times, and I multiplied it by 1/2 since something raised to the half power is the same as square root. So I'm going to add that in a second. First, I'm going to add the parentheses, and I'm going to take the distance vector x, and I'm going to raise it to the second, I'm going to raise it to the second power, and then I'm going to add the y and raise that to the second power, but I'm going to take this whole thing and take the square root of it by raising it, the sum, to the half power. And this is the length of the vector. The next step is to now take that length and actually normalize the vector by dividing each part of it by the length. So you normalize a vector by taking its components, dividing it by the length. So I'm going to do that here. The distance vector is now going to be reset to its old x, distance vector 0, divided by the length, and then its old y, divided by the length. And this is the normalized vector. Its total length is 1. And that makes multiplication really easy because I can now easily multiply a speed. So now what I'm going to do here, if I were to run this, player use... Oh, it didn't want me using this operator here. Let me take a look at what this issue is. All right, so I made two small mistakes. The first one, distvec raised to the second power. That is not correct. I want an index. I have to index it. So distvec 1 raised to the second power. I want x squared plus y squared, and then the whole thing to the half power because that's our formula. The length is the square root of x squared plus y squared. And I just forgot to index the list there. Also, for some reason, I put distvec y. Y is undefined. I meant to put 1. So now the output that we're going to get, since we have the correct world position of the mouse, the correct vector calculated between the world position of the mouse and the player's position, that's why we're using the subtraction. The length here, distvec here, so we have the distance vector and we resized it to the size to the length of 1, but that means that now our player isn't even moving because it's just so small he's not really able to move at all. So, and that's where we are in the step. We resized the vector to a length of 1. Now, by multiplying by a speed variable, we need to make it a little bit bigger. So we took it from the whole thing, resized it to 1, and then since it's easy to multiply by 1, we can now multiply our speed variable into this. So let's do that now. So I'm going to multiply by, say, 3. That's the example I used in Paint. You have to do this with both the x and the y. And now if I run this, we finally have the player following the mouse like so. But it's a bit slow. It's not quite Slither.io speed. I would say I would want maybe, how does 4 look? And 4 looks a bit better. In fact, this is pretty accurate to the game, but since it's, I'm kind of bored at the moment, I'm just going to make it 10. And remember, we want to use a speed variable, and we already have that. So we can just multiply each by self.speed, then self.speed here. And so now the player moves much faster, and we get finally the proper Slither.io movement with the player following the mouse. So good job watching all the way to the end. This was probably my most math intensive tutorial, and I'm pretty sure I won't have any coming up that will be quite as math intensive. So thank you for watching, and then in the next one, I'm going to add body segments so that it's not just the player head floating here.